Hello and welcome back. So in this particular video and perhaps a video series, I will be going through Taylor's Classical Mechanics. I've heard that this is a pretty good book for people who have some very basic experience in, let's say, mechanics, or even some math, but they don't have a very good notion of it and would like to improve. So I think I'm someone of that characterization, so perhaps this book will be useful for me before I get into more serious understanding of physics. Yeah, I think that's about that. I think the last time I left off somewhere around 1.5. I didn't show that in YouTube, but I think hopefully from here I'll start maybe trying to read along as I go on YouTube as well. So yeah, you have Newton's third law, which says that the two forces exerted on the two objects interacting with each other are equal and opposite. And this is sort of both a vector and magnitude, or sorry, I mean like a direction and also magnitude. So there's a force acting along the line joining one and two, or sorry, the force is acting on the central line. Yeah, this is another thing, is that the forces exerted by these two, let's say, our objects are directly reaching out from the center of these objects. Yeah, I think maybe this assumes some sort of equal distribution of density or whatever it is around these two objects, so that their forces are perfectly centered. I'm not sure if that's always the case, yeah, but I don't think that's important. I think for most of beginning physics, people assume that things are uniformly distributed, there's no air resistance, and so on. You get your non-elastic, or is it elastic? The one where you don't lose heat, the collisions. Yeah, I mean, these two objects are fine, but maybe there are external forces too, while these two objects are interacting. So yeah, okay, this one is more interesting. It assumes that the force on object 1, okay, what is F12 again? I keep forgetting it. A force exerted on object 2 by object 1. So this is the force exerted on object 1 by object 2, plus some external forces on object 1. Yeah, that makes sense. Compute the rate of change for particles' momenta using the second law. Yeah, the momentum, which is, I think, your mass times acceleration or something. Yes, yeah, that's the second law, but they rename it to this sort of, this is not really momentum, is it? It's like a derivative of the momentum, because dv dt, I mean, A is dv dt, so this is dp dt kind of, I think. Yeah, that's sort of how it is, I think. So you get that the derivative of momentum is computed according to this. That makes sort of sense. So these two forces exert forces on each other, but they also are pulled by some external force. Looks like towards a common area. Yeah, so okay, so then somehow the book also is interested in the total momentum of the two objects. Perhaps for calculating the total change in the system is also important. There can be some rules made concerning the total momentum in a system. These two cancel out because of Newton's law. Yeah, because these two are opposite, and you're left with the external forces only. Yeah, so in the end, the total momentum is only impacted by the external force. It's not impacted by the interactions within the system. I suspect that this will be true no matter how many different particles you have in the system, but we'll have to perhaps look into that later. Oh, see, yeah, they talk about this. The result is a series of important results. Yeah, internal forces have no effect. Yeah, so if there are no external forces, there's no change in the momentum. There's no dp dt. Yeah. So there's a conservation of momentum. Yeah. Okay, so they have shown it for a system of two particles. Yeah, because I think that by summing up, by computing the total momentum in terms of its component forces, they were able to cancel out these two things, and then they're left with the external. But if you have more than two, that equation maybe can be a little bit more confusing. But I think it's still the same. You just pairwise cancel each other out. The pairwise particle interactions cancel each other out. There's nothing too crazy there. Okay, so here is a particle system. You got your alpha, so the force exerted on alpha by beta, and your external force. Yeah. So I think this is interesting because, like, if you have many external forces, you can just sum them up and get a single external force. And yeah, that's something I didn't really think about. Yeah, so like, okay, alpha, beta are like variables that can take these values and so on. Yeah, so for each particle A, it's a pairwise interaction with all the other particles plus your external force. Yeah, it's summing over the alpha beta, which is ranging over these values, which makes sense. Then you have your momentum over your particle system. Then you can take the derivative on both sides with regards to time. Yeah. And then you can get this general equation, which is adding up all these guys, and then yeah, I think this summation will get computed to 0 because you get, well, first it's looping over all the betas, which is not equal to alpha. Or sorry, first it's choosing which alpha, and then inside that loop it's choosing all the betas which are not equal to that alpha. Yeah, each FAB can cancel out with the FBA. Yeah, if you order them based on like which one has a larger index, then you can pair up the two. Yeah, so in general you can get it as a purely dependent on the external force as well, so that's fine. Principle of conservation of momentum. 0, the momentum is constant. Yep, that makes sense. Oh, wow, this is apparently one of the most important results. It doesn't seem too difficult to understand, but perhaps there's more understanding that comes from relativity or quantum mechanics. Okay, so it says that you should be able to show yourself that the principal conservation of momentum also implies Newton's third law. So how would you go about demonstrating that? What is Newton's third law again? It's this. Okay. Well, I think it's easier to start with only two particles. If two particles, their forces, their momentum, their momentum's derivative with respect to time only depends on the external force, then these two must be opposite to each other in the sum to cancel each other out. And so I guess that makes sense in a rough idea, Idea of Newton's third law. Can taken to be exact. Oh, interesting. So it's kind of an approximation that's exact until you approach light speed. Are equal and opposite. Okay. Yeah, again, like I think one thing that is important to know that the F12 or F21 or F alpha beta is dependent on time also. I tend to forget that is a thing. Yeah, because if the time is not like, somehow like time is, they don't both have the same time of origin, like their T naught is not the same, or you can't even make it so that even if they have different T naught, time is still moving at the same time. Like the time is increasing at the same time for both, or something crazy, I don't know. Yeah, that's pretty weird. I don't know much about that. Okay, so you got your particles with positive charges that produces a magnetic field that exerts a force. I don't know about this. I don't know anything about electromagnetism. So the resulting magnetic forces do not obey Newton's third law. Okay. So it's saying that the magnetic forces exerted by the magnetic fields of the positive charges don't act in the same way, like for example as your gravitational force or something. Okay, so it says that the Q1 is moving X direction and Q2 is moving in Y direction, and they produce a magnetic field. Is it B? And then B of Q2 and B of Q1 exert a force F12, F21 on the other particle or something. With the right hand rule. Something like that. I don't know. Yeah. So I guess for like when you're talking about this magnetic force, the momentum is not conserved. So yeah, the mechanical momentum, so the velocity, purely driven by mechanics. The electromagnetic field also carry momentum. Okay, see. The mechanical momentum being lost by the two particles is going to the electromagnetic momentum of the field. Okay, geez, yeah. I wonder if there's something to do with the fact that energy cannot be destroyed, or if you relate energy to momentum, and then momentum also cannot be destroyed, only transferred to other forms of momentum. But I don't know much about that. Both speeds are much less than the speed of light. The loss of mechanical momentum and what the heck is this concomitant failure of the third law completely negligible. So not much of the momentum of the particle is being lost to the magnetic momentum. So you can almost approximate it as entirely mechanical. So it sort of works well with Newton's third law. I can see why this would be useful, because in terms of computations, if you don't need that many significant digits. You can certainly neglect the effects that don't have that much of an impact. Yeah. Okay, so this is a Coulomb force. So the Coulomb force, the electrostatic force does obey Newton's third law. And the magnetic force is of order v squared over c squared of the Coulomb force. Okay, I see. But if the Coulomb force is significant and v is close to c, then it can be noted that the magnetic force would also be significant. It would be close to around the same as the Coulomb force. But since you know c is like, what, 3 times 10 to the 9th meters per second, any velocity we see in daily life would be negligible compared to that. So see, the unexpected situation does not contradict our claim in the classical domains. Newton's third law is valid. Yeah, so if you don't consider like the magnetic stuff, it will be fine, it seems. Yeah, just concerning the, and if you don't go too close to light speed, you won't lose much to the magnetic stuff anyway. That's what it's saying, I think. Equation of motion. No practical use on this. What is the first law again? I keep forgetting this. Keep having to go back. A constant velocity. Okay, without any force, it's constant. Yeah, I think that relates to the second law. Without any force, the acceleration is 0, so velocity is constant. So, yeah. The third law is crucially important to learn out the internal forces of a multi-particle system, but once you know the force involved, the second law is what you actually use. Okay, yeah, that makes sense. The second law has an actual equation. Okay, so r is a position vector, I see. Okay, it's a second order derivative of the position that gives your acceleration. You want to solve for r. Okay. So you know f, which means you know a, the acceleration a, and you want to use a to solve r double prime, which is your differential equation. Or sometimes you know r and you differentiate twice to get the force. Yeah, that makes sense. Yeah, resolve them to their chosen coordinate system. Okay, I see. Yeah, I think this makes sense. Nothing too crazy about that. Yeah, differentiate twice, you'll get the acceleration in terms of its components, which will be equivalent to this f, I think, or if you multiply by the mass. Oh, yeah, okay. So this, I think, resolves really well because it's in rectangular coordinates, I think, so that it looks nice, but I don't know if it will be the same for like spherical or radial or whatever other coordinates you have. Okay, and they have a nice example. Let's take a look. A block of mass m is observed accelerating from rest down an incline that has a coefficient of friction mu, an angle theta from horizontal. How far will travel? Yeah, I haven't solved physics problems in such a long time. Yeah, I think I'll screw up so much in this. I choose a frame of reference. So it's the starting position, it's the frame of reference, origin of time. Yeah, one normal and one across. Okay, so yeah, and what's the one across it? I guess it's like this, I don't know, coming out of the page. Yeah, only x varies, y doesn't vary at all. Two of the three forces on the block are unknown, the normal force and the friction. Wait, wouldn't this mean that two of the three forces are known? I guess that's a typo, right? The normal force is in the y direction, and F is in the negative x direction. Okay. So there's no force in the z direction. Yeah, there's no force coming out of the page, so there's no acceleration, and there's no change in position. Yeah, for z. Yeah, so just consider the xy. And there's also no change in position for y. Yeah, that makes sense. But they can use it to actually compute something. So there are two forces acting in the y direction. One is your normal force and one is your weight. If you use some like similar triangle stuff, you can see like this angle is theta. And so mg cosine theta is the angle, is the magnitude of the force pointing downwards against the plane. Those two planes sum up to 0. So you can get some information about the normal force, I think. Yeah, the normal force is mg cosine theta. Okay, so F is mu, and yeah, I don't know any of this. I think I probably remembered this at some point in my life, like maybe 8-9 years ago. Yeah, friction force is the friction coefficient times the normal force. Then you get this, the x component finally. Okay, getting into the x component. Because we are trying to solve for how much time it takes, or not how much, how far it will travel in time t. I guess you integrate over the position derivative for the time it would take from 0 to t or something. Okay, I guess they're solving for x, right? From using the differential equations thing. What is this? So in the x direction, there are two forces acting. One is mg sine theta, and then another one is your oh geez, my brain. Yeah, mg sine theta and f. Yeah. So the m's cancel. Okay. So okay, so you like anti-differentiate twice or integrate twice to find out about your position function. But first you only have a positional, like secondary, what is it called? Second order derivative. Okay, that's why you're able to say it's equal to this times t, because the initial velocity is 0. Okay. And the same, since the original position is 0, that you can do this without adding another constant. Oh, okay, and you just plug in t. Okay, that makes much more sense. Yeah, polar coordinates. Yeah, this is completely reasonable. Nothing crazy about this, I think. So I wonder what the point is behind the actual usage of polar. I know in maths what the point is, but in physics, I don't know, which I think is a shame. Oh, yeah, this phi hat is interesting. Yeah, I didn't know this. Like it's the direction tangential to like your circle or your change, whatever the direction you were moving in, I guess. Or not necessarily, like something like that. Yeah, I guess depending on how the vector r is oriented, the r pointing out, the r hat pointing out of it would change, and depending on which direction or where the, I guess, wait, how's this phi hat defined again? Phi increases with r fixed. Okay, so it's the direction that's tangent to your change of phi. I guess this is it's the vector tangent to the circle when you draw from increasing phi around the center with radius r or something weird. Okay, so the force is written in terms of, because these two are perpendicular to each other, you can always decompose force in terms of purely the two perpendicular ones, I think. Okay, yeah, that's exactly what they're saying. Yep. It's sort of like XY, I think, but just slightly different reference frame, I guess. I don't know. Fr is the tension on the string. Fi is the force of air resistance. Okay. Yep. Oh boy. Oh, and that's it. Okay, but they have cylindrical too. Cylindrical force too. I think I'll take a small break because this is looking a bit intimidating and I'm running low on sleep.